My name is Suri Wang. The topic of my presentation is GPUpd, a fast and scalable multi-GPU architecture using cooperative projection and distribution. Graphics processing unit vendors have been scaling single GPU architectures to satisfy the ever-increasing user demands for faster graphics processing. However, as it gets extremely difficult to further scale single GPU architectures, the vendors are aiming to achieve the scaled performance by simultaneously using multiple GPUs. Unfortunately, the scalability of current split-frame rendering implementations is seriously limited, as they suffer from a large amount of redundant computation among GPUs. As a result, this paper proposed GPUpd, a novel multi-GPU architecture for fast and scalable split-frame rendering. GPUpd also introduced a new graphics pipeline stage called Cooperative Projection and Distribution, where all GPU can cooperatively project 3D objects to 2D screen and efficiently redistribute the objects to their corresponding GPUs. So first, I will introduce the background of this project. In this figure, it shows the graphics pipeline defined by DirectX 11 Graphics API. From this figure, we can see that these pipeline stages can be mainly grouped into three categories. The first is the geometry processing category. Geometry processing step projects vertices in a 3D object space to the 2D screen space and groups the vertices into primitives, which is the basic elements GPUs operate on, typically triangles. The step consists of input assembler, vertex shader, height shader, tessellator, domain shader, and geometry shader. The second and the third categories are called rasterization and fragment processing. Rasterization and fragment processing generate pixels from the primitives processed by geometry processing. First, the rasterizer stage converts primitives into fragments, which will be used to produce pixels. Second, pixel shader stage calculates per fragment attributes such as color and dips. Third, output merger stage determines if a fragment is necessary to produce a frame, and generates pixels from the necessary fragments. After the pipeline, I will introduce the microarchitecture of a GPU. In this figure, it shows the NVIDIA GP104 microarchitecture of recent NVIDIA Pascal GPUs. It consists of graphics processing clusters, GPCs, render output units, RLPs, L2 caches, memory controllers, a gigathread engine, and interfaces to CPU and other GPUs. GPCs perform computational tasks such as shader execution. Each GPC consists of a raster engine, a hardware unit for rasterization, and texture processor clusters, TPCs. Each TPC contains a polymorph engine, PME, and a streaming multiprocessor, SM, consisting of computational resources. GPU memory contents, such as textures and frame buffers, are interleaved across memory partitions to increase memory bandwidth. Each memory controller is paired to an L2 cache, and multiple RLPs are associated to each L2 cache. RLPs validate pixels generated by GPCs via dips and alpha tests, and update the frame buffer with valid pixels. In this figure, it shows how the graphic pipeline is executed on top of the baseline GPU microarchitecture when an optional geometry shader is enabled. When an application issues a draw command, the gigathread engine receives application-issued primitives and distributes them across GPCs. Then each TPC fetches vertex data using the vertex fetch unit, executes vertex shader and geometry shader on SMs, and calculates per primitive screen space coordinates using the simultaneous multi-projection unit. The processed primitives are then distributed across GPCs and get rasterized into fragments by per GPC REs. After that, a TPC setups per primitive attributes using the attribute setup unit, executes pixel shader on SMs, and distributes fragments across RLPs according to their screen space coordinates. Finally, each RLP validates the fragments and updates frame buffer using valid fragments. So after the background, I will introduce the main part of this project. First, I will introduce the Cooperative Projection and Distribution Pipeline, or CPD pipeline. This pipeline is used for fast and scalable split frame render before geometry processing stage of the original graphic pipelines. CPD consists of two phases: Cooperative Projection CP and Cooperative Distribution CD phases. By looking into the figures below, comparing the first three of them, we can see that though the number of GPUs increases, the latency is not reduced, as the critical path on geometry processing is not changed. However, when we implement CPD, we can achieve several advantages. First, CPD accelerates geometry processing by minimizing the number of primitives each GPU processes. Moreover, since each primitive is independent from others, CP phase can scale on multi-GPUs. Geometry processing latency linearly decreases as the number of GPUs increases. This can be seen from the D and E figures. After introducing the pipeline, I will introduce the architecture of GPUpd. GPUpd is a novel and scalable multi-GPU architecture that implements CPD. First, look at this figure. This is the execution flow of the graphics pipeline on GPUpd. The numbers next to the hardware components denote corresponding graphics pipeline stage in the first figure, and the 0 stage denotes CPD. To introduce the GPUpd architecture, there are four main parts that might need detailed introduction. The first part is the software extensions. This is used when an application issues a draw command. Then GPUpd begins CP phases by evenly distributing primitives to GPUs. For the second part, hardware extension. First, because GPU needs to identify the list of GPUs demanding a primitive to correctly process its frame region. Therefore, a new hardware unit is necessary, since the baseline GPU microarchitecture lacks relevant hardware units. Therefore, GPUpd as a primitive to GPU mapper, or P2G unit, to each PME. Secondly, to avoid large implementation costs, GPUpd as a primitive exchanger, PE unit, to each GPU. PE units exchange primitive IDs between them by exploiting the way the extended API runtime distributes primitives to GPUs to eliminate the need for large on-chip storage. In the third part, the inter-GPU communication optimizations, there are mainly two methods. The first one is draw command batching. This is used for reducing inter-GPU synchronizations. And the second method is the run-ahead execution. This is used to further improve single frame latency by utilizing the idle resources. The fourth part is the tiled-based rendering architectures. These architectures employ a two-step execution model with an on-chip Z buffer and frame buffer to reduce off-chip memory bandwidth consumptions.